everyone. Thanks for joining this presentation on crack repair. We're going to talk about performance characteristics for concrete injections. We're going to mainly focus on the normative framework, which defines and classifies the materials used in crack repair these days. So before we start the presentation, I would like to thank the Neville Center for the invitation. And it's actually quite interesting that we are also providing presentations on very practical subjects, and this is one of them, I believe. And there's a little bit of confusion sometimes, and I hope that the measures and the application rules that I'm gonna share will help you going forward. So first of all, a disclaimer. Bear in mind that this presentation is intended for educational purposes only, and it's been prepared by myself. The information is given in summary form and does not really it doesn't need to be complete, but we believe that the examples given are represent best industry guidance, although you should not consider these as advice or recommendation for a particular project you are involved with. In terms of agenda, the subjects that we have here to discuss, we will first of all discuss the basics of concrete repair and how concrete repair is introduced in the European normative framework, which is the EN 1504. We will discuss the two basic principles of concrete repair involving injections. The first principle is the protection against ingress, or P1, and the second is the structural strengthening, P4. And we also talk about the different materials and uses of injection filling materials. We'll discuss a little bit the application conditions, and there are some materials that have a better range of applications than others. We'll briefly touch base on quality assurance, and finally we'll kind of highlight, the most important considerations. So first of all, introduction to concrete repair. It's a very broad subject. As you can see, it involves several products, from surface protection to repair mortars, bonding materials, injection materials, anchoring products, and coatings. The rules of application and are actually described in Part 10, but the principles for the use of each product are in Part 9. Now, there are associated tests with all of these materials, but they are kind of more focused on the production. So for manufacturing, they will have to comply with these products in order to seek certification. And in terms of quality control of the products, also for the manufacturing point of view, we have 1504 Part 8. But for us, we'll focus more on the site application, Part 10, and also the principles, Part 9. Now, we should bear in mind that when we have to decide on an appropriate action to meet the future requirements of a particular structure, there's a couple of steps that we always need to bear in mind. And sometimes the most important is to just do nothing for a certain time. And this is particularly relevant for crack repair, because there are some that cannot really be applied unless the crack is dormant. If the crack is moving, and we use certain types of crack materials, actually applying that material will result in additional cracks. So this is also important to sometimes do nothing for a certain time, assess the situation, confirm that the crack is not moving, and then really decide on the next steps. The second step is to reanalyze structural capacity. Is the crack really interfering in the structural capacity? Are we getting a loss of load carrying capacity? And then the third one, I apologize, the third one, and perhaps also quite important from the point of view of waterproofing, is to prevent or reduce further deterioration. We all know that water brings aggressive chemicals and also ex accelerates corrosion. So it's also interesting to know whether or not we should stop the immediately water ingress. Now, if we start with the basics of concrete repair, we can see that there's a little bit of systematics in the approach in accordance with the standard. So first of all, and highly recommended, is to carry on with the condition assessment protocol. And now also to going forward, we start to think about the selection, the selection of the intervention approach. Again, doing nothing, is it the repair, is it the demolition? Once this is defined, we can start to identify the repair principles, assuming we are not we are repairing. The repair principles that and I only listed the ones associated with injections, is the protection against ingress and the structural strengthening. And then we can select the repair method. So for each of these principles, there are repair methods associated. And actually, we should remember P1 and M1.5, M4.5, for example, which is injection cracks, voids, or interstices. This is quite interesting because when we are specifying the material or the strategy, we also should also refer back to these kind of codes because they kind of mean they really represent the prescription by the designer or by the specifier. So, and this actually helps us selecting the best suitable product because we know that they've been certified to meet that use case. Once we select and we go through the principles and the repair methods, we then can start to specify the repair material more in detail. For example, do we want a repair material to just allow transmission of forces across the cracked surfaces? Do we want a material that is a little bit ductile and allows movement, or do we want something that swells upon contact with water? We can also specify the temperature range of application. Do we want to inject in the cold weather because the cracks are 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 the biggest, and also at the time because it's quite low temperature, you should also specify the minimum temperature. So all of this is quite important. And in the end, we can also try to specify the frequency of inspection and any maintenance requirements. Um, The basic and perhaps the most used case for the crack repairs is they are always associated with the protection against ingress, and waterproofing actually plays a role over here. So method 1.5, filling of cracks, is, as we can see, is all about in filling the void or the crack with a suitable material that prevents water and aggressive agents to come inside. So the objective is always to fill with a suitable material. The aim is not to increase load bearing capacity because we are just focusing on principle number one. The materials in theory should be very ductile, so in a way to allow certain extension of flexibility, also because of thermal contraction and thermal extension, they should be flexible and allow for crack movements. But in another way, if we're talking about a big joint, large crack movements are not really the case. So we need to use other methods. But when correctly utilized, it actually prevents water from entering the structure and can act as a permanent waterproofing. The fundamental characteristic of these products is that they allow reinjection over time. In terms of structural strengthening, this is another method. So structural strengthening, although we not really believe that a crack on its own can strengthen a structure, but the main objective is actually to make sure that we can fill these cracks and they can transmit forces across the crack surface. So in order to do that, there's only two sorts of materials that are able to provide a function. And so of course, epoxies, as everyone knows, and also cementitious materials. So the objective is then to obtain a full transmission of ductile and tensile forces over the defect areas. This means that the injection material should be able to fill the crack as completely as possible and have sufficient compressive, tensile, and adhesion strength in the concrete. Focused on this reason as completely as possible. This is one of the fundamental differences between this use case and the previous one, in the sense that from a quality control perspective, we may have to extract cores to really verify that we are indeed, providing structural strengthening. In terms of materials and the use cases, um, we will span across several materials. And in terms of protection against ingress, perhaps the most widely known is polyurethane. So polyurethanes can be designed from soft, elastic, flexible, can be rigid. There are now some polyurethane materials which can also be used in terms of structural strengthening for in certain occasions. They bond very well to dry and even wet surfaces. So if your objective as consultant or providing advice to project is to recommend something that prevents water ingress, polyurethane will be the go-to choice. It's also cost effective. It also produces less heat, and it's not corrosive to steel reinforcement. The specification, as I described in the deliverables before, it's all about the use and the workability, W. So use meaning D is ductile, D1 is the specific class. Workability as 2 means that the minimum injected crack width is 0.2 millimeters. And then the third group here in the specification is all about the conditions of the crack. Is the crack dry? Means 1. Is the crack um, some kind of with some moisture, which is 2, or is the crack wet, which is 3? And then the fourth group is the minimum and maximum temperature. This is important because it allows you to plan the work and play with the pot lives, basically. I'm not sure if I can just put this video over here to show a little bit of the how we can inject in structures. So polyurethanes are basically a resin material. They are plastics. They can extend and contract up to a certain degree. These particular ones that don't swell in contact with water, but they are capable of accommodating structure movements. So very difference between these and the epoxies is that we generally tend to use steel packers. So injection packers are inserted across the different sides of the crack, following specific pattern. Usually the distance between packers is about half the thickness of the element that we are injecting. And then we fill the crack. Now, if we focus on also another set of materials used for filling of cracks, we have the acrylate gels, which they kind of allow you to create a curtain effect by sealing the cracks, but also behind the cracks. So it creates almost a waterproofing layer. This particular product is used to um, repair damaged PVC layers, for example, or TPO layers. So it's an interesting solution. In terms of structural strengthening, we have the cement-based materials and epoxies. So usually only epoxies or cement-based injection systems, being either paste systems or cement suspension or micro cements, may be injected to ensure transmission across the cracked surfaces. So for cement suspensions, we will be talking about ultrafine cement. So it's quite important to ask the manufacturer for the the finest level of the cement, and also to work about in terms of additives and water, because in really high temperature climates, your workability time gets short. For cement paste, this is more to inject large crack widths, for example, maybe in some dam projects that are suffering from ASR. This is probably an interesting solution. And for epoxies, we are talking about cold curing two-component resins that are injected. These are probably the most widely used in the market available today. But bear in mind one thing: you cannot really inject large cavities with epoxies. The reason being that, one, the E modulus is quite low, so it will never be representative of the material that you want to repair. And second, and perhaps most important, is that epoxies, when they cure, they can develop high temperature. So, and you don't want to get high stress levels. So be careful with the use of epoxies over large volumes. The perhaps the most interesting part of epoxies is that although really um, um, they don't really um, accommodate long-term movements, they can accommodate short-term movements in the sense that they are kind of dynamic resistant. So when you are specifying um, epoxy materials, you can see that there is a fifth group over here, which where we can actually be more precise and say that you want the material to withstand daily movements up to a certain percentage. So that's why you put the one here, which is 10%. But again, very important to note, epoxy should only be used in dormant cracks they don't change the crack width often, and but can accommodate slightly small movements because of vibration and so forth. This is probably of interest for wind energy towers or wind energy foundations, if you really want to reinstate capacity across the crack. Now, perhaps this is a quite interesting chart in terms of application conditions. Um, we need to. This was extracted from um, the um, the German code of practice, which eventually led to the European standard. Um, so we can see that there are several filling objectives. So this is almost like a wrap up of the presentation in a way. So closure, we basically want to limit the crack width by filling. Um, the other objective could be waterproofing. We can also we may also wish to ensure bonding, and or we may also want to ensure some limited ductility. So if we focused on the waterproofing, which is perhaps one of the most important use cases, we can see that epoxies really only work well in dry. Most of 100% of the epoxies work only in dry situations. Some epoxies may work in damp situations. Cement, we can really waterproof a structure in most of the conditions, except if we have flowing water. So careful with this. But polyurethane is really a wide range, from dry to flowing water. It works. Um, Now, if we really want to ensure transmission of stresses across crack surfaces, then we may wish to use epoxies or cement. The issue with cements is that they need a little bit of a higher crack width. So, for example, at least 0.3 millimeters or even more, 0.5 millimeters at the minimum. For suspensions, if you want to use paste, you probably need a really large, a big one. But they do allow injection on several um, substrate conditions. Now, the epoxies, you really need to wait for a dry situation to inject the crack. But also epoxies, they can work from very low crack widths, um, 0.1, for example, 0.2, 0.3, 0.4. But again, if we have a thick section of crack or joint to repair, it's probably not recommended to use epoxies. Yeah, so this is quite an interesting table. The perhaps the other table that I also want to share is basically a summary of all the application conditions appropriate for cements, epoxies, and expandable materials such as polyurethane. So, as cements can be used to fill voids, epoxies not really because of the reasons already discussed. And polyurethanes, yes, we can also do large volume grouting with polyurethanes. Because of the cracks, uh, with cements, you can just fill most of the cracks with cement. It's compatible with apparent concrete. Epoxies, always if the cause of the crack is known and non-recurring, this means that the crack there's no movement, so the crack is dormant. Flexible, it doesn't really matter. The cracks may reappear, and the fact that they can change conditions also allow the polyurethanes to be re-injected because they accommodate movement very well. They bond against new crack surfaces, but um, they also bond against um, the polyurethanes themselves. Um, this is where things also get a little bit interesting. Sometimes we are called to advise on situations where cracks have already been injected, and because they have been injected, um, we have limited mitigation now or correction measures. Because if we are in a situation where the main objective is to ensure what the tightness of the structure, and that crack was already injected with epoxy materials, we can use flexible polyurethanes. But for example, if we decide otherwise, if we decide that actually structural capacity across the crack is important, and we filled with polyurethane, we cannot apply epoxies or cement. So you need to be sure, um, I think from the start, what's the right product to be used. In terms of dynamic cracks, cements don't really accommodate the movement. Epoxies do for reduced crack widths, mostly on transient and daily changes, but they need to be within a certain value. And I guess here you are playing with the elastic modulus of the epoxy, which is considerably less than concrete. But if we have flexible materials such as polyurethanes, of course, this is permitted. Moisture condition, as discussed before, cement can accommodate from dry to wet conditions. Epoxies mostly dry, some damp, and polyurethanes any range from dry to running water, flushing water. Minimum temperature is also quite important. If you are planning your injection campaign, it's quite interesting to target these for the coldest temperatures, just because the cracks will be the highest. But on the other side, you also need to understand that the workability time is different. So be mindful of this. Injectability, basically means which material can fill the minimum crack width. So we can inject up to down to 0.5 millimeters with cements, epoxy 0.1, although we know that water is only water only flows above 0.3 millimeters, but epoxies go up to 0.1. and there's nothing that goes less than that, by the way. And polyurethane is really, the standard is 0.2 millimeters, so quite a good range over here. Um, Quite also important to understand is the change of width during curing phase. So in cements, you need to be sure that the structure is not moving. If necessary, you may have to, for example, in wind energy applications, you may have to stop the structure from operating. Epoxies, you do allow some movements, but this requires a very sophisticated understanding of the crack with changes. So it's always recommended when you apply epoxies to actually have a monitoring or a seasonal monitoring of the crack with changes, so that you know that what you are applying will be correct. And flexible doesn't really matter. They accommodate very wide ranges of crack width changes, and they also allow for re-injection. A crack width variation during the useful life, um, also, of course, we cannot accept crack width changes with cement applications. Epoxies also, we cannot accept these changes um, unless there are some limited variations, but I think it's quite minimal. So careful with this, and also always seek for the manufacturer's recommendation. And in terms of flexible, we do have several limits, but until when you can basically lose your water tightness, basically. So all in all, I believe this table is quite um, speaks for itself in a way. It's self-explanatory. It's also based on the work by the German code. Um, so I highly recommend to have a look at it. So now in terms of quality assurance, um, perhaps design assurance is an interesting point, because when we plan such an intervention, we should really understand whether the cracks are moving or not. So this is fundamental. And with if we answer this question, we can already identify the materials that will be most appropriate. Um, in a way, if we use epoxies to inject moving cracks, we will be asking for trouble, because new cracks will form. Now, the market has several materials available, so you can always tailor you can always find these to match your particular project specific requirement. Um, you can do check tests. So when you do a particular injection plan, you should always do some checks to verify that it's working. Destructive testing in this case involves the extraction, of course, so that you can really find out whether the degree of filling is complete or not. Usually 80, 70, 90% depends of your conditions. But at least during a trial, you should really do this to prove to the client, to the asset owner, that your injection strategy is working. So in the end, the quality of the crack filler can only be determined by removing cores. Very important as well, although not mentioned, is the documentation. So the German code actually gives you on the back and as an appendix several working sheets that the contractors should be using to record and log their their work. And this is quite important, because it brings a systematic approach to crack filling. So focus on quality and on your inspection and test plans. In terms of concluding remarks, the products for crack filling are standardized, so it's very easy to pick the standard and even specify any product according to the standard. They all show classification systems, so this makes life considerably easier for engineers and specifiers and consultants to really target and fine-tune their products, because it's it's not a manufacturer secret anymore. There's a structure to specify. They are the main products available in the market these days address force transmitting, ductile, swelling, and swelling filling materials. The filling method and crack filler used depend on the minimum crack widths that you wish to attain. This condition applies accordingly to filling of cavities, and injection into cavities proposes that crack filler can penetrate the damaged area. So also this is a specific area of interest. Do a little bit more research into this, and it's fundamental that the crack movement condition is established before selection the appropriate repair method. Focused more on the investigation, focused more on establishing the range of variance of the crack, and if if necessary, install instrumentation to select a repair strategy. This is something we've done, and we highly recommend being done, so that you can select the best approach to your project. Well, I hope I have given a bit of a helicopter view of the of the kind of the injection systems used for structural strengthening and for protection against ingress, and I hope this is helpful in your in your future work. Thank you very much. My name is Nuno Ferreira, and I've been working with Arab for 8 years. My focus is on concrete, and sometimes we need to learn about specific areas to make sure that the concrete lives a bit longer. Thank you again, and please reach out to me if you wish so. Thank you so much. Bye bye.